Hello, ninth grade extended students. Today we are going to talk about the minimum number of line reflections needed to create unique isometries. As we talked about in our last lesson, we have decided that congruence is defined based upon whether or not there is an isometry that will map one figure to the other. So we are just giving this a little bit more formality here, in that this is our congruent symbol. The subscript pi means it's of the plane. You could substitute of space. Sometimes we just leave pi out when it's understood. And what this says, and it's our definition, if pi is a plane and A and B are figures in pi, then A is congruent to B if and only if there is an isometry F that's an element of the set of all isometries of the plane. Remember, that's a fixed number of line reflections, such that A gets mapped to B. We read this as A is congruent to B. Next, I'd like to talk about congruence as a relation. So remember, a relation is a set of ordered pairs, and in order to be in the congruence relation, the ordered pairs are figures of the plane. So it's the set of ordered pairs A comma B, where A and B are figures in the plane, and A is congruent to B. So let's look at this. In order to be an equivalence relation, it must be reflexive, symmetric, and transitive. So in order to be reflexive, it means that every element has to get mapped back to itself. Well, let's think about what this congruence relation is. This says in order for A comma A to be in the relation, that means that A must be congruent to itself. Well, that's surely the case because I can map every figure back to itself through the identity relation on pi. So it is absolutely reflexive. Next, it must be symmetric. In order for a relation to be symmetric, if A comma B is an element of my relation, then B comma A must be an element of my relation, and in this case, the congruence relation. Now, to be in the congruence relation, that says if A is congruent to B, then B is congruent to A. Now, think about it. If there is an isometry that will map A to B by reflection over lines, then there is an isometry that will map B back to A. All I have to do is reverse the order in which I reflect. So it's also symmetric. And then finally, it has to be transitive. In order for it to be transitive, if A comma B is an element of my congruence relation and B comma C is an element of my congruence relation, then in all cases, A comma C also has to be an element of my congruence relation. Well, let's think about how that's true. If A is congruent to B, that means that there is an isometry that will map A to B. If B is congruent to C, there's an isometry that will map B to C. Therefore, there must be an isometry that will map A to C. All I have to do is compose these and reflect the same way I would to get to B, and then continue my line reflections to get to C. So the congruence relation is an equivalence relation because it's reflexive, it's symmetric, and it is transitive. The equivalence classes of the congruence relation consists of partitions of the set of all figures. So if you can imagine all figures of the plane, you're going to group all figures with their congruent pieces. So every set of congruent figures creates an equivalence class. One way we can categorize isometries is whether they are even or odd. So Even number of isometries are reflection over an even number of lines. Odd is reflection over an odd number of lines. So which isometries have we studied that are even and which are odd, do you think? Remember that reflection is odd. And the other one that's odd is a glide reflection. That's a translation composed with a reflection. The even ones that we've studied so far are rotation, both involuntary and non-involuntary. So we would have all rotations, including half turns, and also translations. So again, an odd isometry are those that can be expressed as the composite of an odd number of reflections. An even one can be expressed as an even number of reflections. And here is a list as well stating which isometries are even and which are odd. And I'm also going to add glide reflection here. I can compose isometries together. If I compose two even isometries, I get an even number. If I compose an even with an odd, I get an odd. Both orders, odd with even, odd. If I compose two odd isometries together, I get an even isometry. ISO 1 says if two isometries of a plane agree on three non-collinear points, then they must be equal. So in other words, if I have two random isometries and I see that I have three non-collinear points and they get mapped to the same location under both, they are equivalent isometries. Let's read through the exact definitions. We're going to let P, Q, and R be distinct non-collinear points of the plane, and let F and G be isometries of pi such that F of P equals G of P, F of Q equals G of Q, and F of R equals G of R. And for all x in the plane, F of x equals G of x, that is, F is equal to G. I can create the same movement by applying either F or G isometries. This is the result of exercise 14. We're going to let pi be a plane, and we're going to let F be an isometry of the plane. If two distinct points of pi are fixed points of F, then every point of the line they determine is also a fixed point. So let's think about why this is true. Remember, an isometry is the composite of line reflections. So if I have two distinct points that are fixed, remember the only points that are fixed under line reflections are points on the line of reflection. So if I have two distinct points of pi that are fixed points, then every point of the line that they determine is also a fixed point of the isometry F. So far, we've only studied isometries that have at most two line reflections. And it just so happens that we could have any number of line reflections. So I could have reflections over 4 lines, 5 lines, etc. You might remember in our last lesson, we were able to find an isometry that mapped one segment to the other, and I was able to do it in 2 reflections. I could have used more, but we're able to do various isometries in at most 3 line reflections. So let's see what ISO 2 says. It says every isometry of the plane is either a reflection or a composite of 2 or 3 reflections of pi. That is, no matter how many reflections of pi are composed, the resulting isometry is equal to the composite of at most 3 reflections. So, in other words, I can create the same movement by reflecting over 3 lines. I don't ever need more than 3 reflections to get one object to move to the other if they're congruent. ISO 3 says every even isometry of the plane is the composite of 2 reflections of pi. So, in other words, if it's even, I can always find exactly 2 lines to reflect over that would create the desired movement. If it's odd, it's either a reflection of just 1 reflection or it's the composite of 3 reflections. And because of this is going to break down quite nicely. There's only a certain number of isometries that I can have. The even ones are going to be rotations. I'll write half turns as separate, but they're kind of the same thing. And translations. The odd would either just be a plain reflection or a glide reflection. In your book, in EMF, there is a reflection experimentation tool to help you through exercises 18 through 23. I'd like you to experiment to see what types of isometries are created by reflection over 4 lines. Remember, if it's even, I can always create the isometry using reflections over 2 lines. So you're going to look and see there's 4 lines. In fact, what kind of isometry does that create? Does it create a rotation? Does it create a half turn? Does it create a translation? So check that out, and also look on Schoology for your assignment. Remember, you do have a cumulative algebra quiz coming up, and there's practice posted for you. Have a great day.